So today we'll discuss non-linear partial differential equations. Partial differential equations. As I mentioned earlier, we will be using Char-Pitts method here. Char-Pitts method. So non-linear partial differential equations means P into P, Q into Q, P into Q, like that. Okay. So P squares, P cubes, or Q squares, Q cubes, or P into Q, because we are in first order non-linear. Okay. All such partial differential equations look in the form of a function of x's, y's, z's, p's and q's equal to 0. X's, y's, z's, p's and q's. So since it's a function of x, y, z, p's and q's also, I can have anything p square, p cubes, q squares, q cubes, and p into q's or whatever. Okay. So all such things are available in this. So at the same time, if you remember z into p, if I have just z into p, it is linear only. If you look at linear partial differential equation, z into p or z into q, though it is dependent variable and its derivative, but still it is linear there. Okay, because in the partial differential equations, the non-linearity comes with product of derivatives, not dependent variable and its derivative. Okay, only product of derivatives. So this can be, sometimes can be a linear also, but in general, if I take this as some kind of an equation of first order, any first order partial differential equation if I have, that can be solved by using Char-Pitts method. Okay. Now, before going to Char-Pitts method, I just want to again clarify certain things. When it comes to partial differential equation, how to classify solutions. Take this one, classification of solutions. Classification of solutions. First of all, solution is any relationship between x's, y's and z's which satisfies the differential equation is a solution. We know it already. Okay. But since in the first order, I have two independent variables in the first order, if I try to solve this, maybe first I will integrate with respect to x, which gives me one arbitrary constant. And again, if I integrate with respect to y, it gives me another arbitrary constant. Therefore, if I try to actually solve this one, which gives a solution which contains those two arbitrary constants, then we call it as a complete solution. Take this one. First one, complete solution. Complete solution. Any solution of the form g of x comma y comma z comma a comma b equal to 0, any solution of the form g of x comma y comma z which contains as many arbitrary constants as the number of independent variables. Because since we are in first order and I have two independent variables, in the first order I can accept two arbitrary constants. Okay. So which contains as many arbitrary constants as the number of independent variables is called complete solution. Is called complete solution. Is called complete solution. Complete solution. I think this is something which everyone knows this. Even ODE also we discussed a similar kind of a thing. Okay. In ODE, since it was only one first order. Okay, it is it is only one independent variable. Depending upon the order of the differential equation, we will have those many arbitrary constants in its complete solution in the case of ODE. But in the case of PDE, since I have more than one independent variable, as of now I have two independent variables. Therefore, my complete solution in the case of first order will have two arbitrary constants. Okay. Second one, general solution. General solution. Bringing relationship between the arbitrary constants. Bringing relationship between the arbitrary constants in the complete solution. In the complete solution. In the complete solution gives the general solution. Gives the general solution. It will be of the form g of x's, y's, z's, suppose a, some function of a equal to 0. Suppose b, if I am able to write as some function of a, one of the arbitrary constants, if I am able to write it as a function of another arbitrary constant. For example, if you see Lagrange's method actually gives you general solution. Why? It gives relationship between C1 and C2. Phi of C1 comma C2 equal to 0, or u equal to phi of v, or phi of u comma v. What is u? U equal to C1, and what is v? V equal to C2. So phi of C1 comma C2 or phi of u comma v equal to 0 gives us the general solution. If you remember in Lagrange's method, every time we talked about general solution, we never ever talked about complete solution in the case of Lagrange's method. But the complete solution is actually obtained from Char-Pitt's method actually. Getting that? Fine. Anyway, we'll discuss that later on, what is the Char-Pitt's method and how to go about the Char-Pitt's method. So what we have to do is, if you can bring about relationship between those two arbitrary constants a and b, then what we get is a general solution. Later on, we'll extend this discussion also in general solution. There is something called as a developable surface belonging to general solution. Developable surface belonging to general solution, wherein I will take one relationship between the arbitrary constants. Suppose phi of a equal to a, suppose, just giving one example, phi of a equal to a. Then, if I partially differentiate this with respect to a and eliminate a from this and whatever the partial differentiation, dou g by dou a equal to 0, which gives us a developable surface actually. Of course, it also does not contain any arbitrary constant, it's a different thing. Okay? That developable surface belonging to general solution only. Anyway. Third one, particular solution. Particular solution. Giving particular values to the arbitrary constants. Giving particular values to the arbitrary constants in the complete solution. Giving particular values to the arbitrary constants in the complete solution gives particular solution. Gives particular solution. In fact, particular solution is a particular member of the family, and he is a particular surface. Member means all members are surfaces only. So if in the given family or in the complete solution, which gives me infinite number of surfaces in the family, of which if I can identify one particular surface by giving particular values to these two arbitrary constants, that is called a particular solution, or in fact we call it as a particular surface also, right? Okay. Last one is called as singular solution. Very important one. Singular solution. Take a note of this. It is a solution which do not contain any arbitrary constants. It is a solution which do not contain any arbitrary constants. In general, it is not a particular case of, in general, it is not a particular case of complete solution. In fact, this is the same definition I have given you even in ODE also. It's the same definition. But how this solution which do not contain any arbitrary constants, in general it is not a particular case. When I mention in general it is not a particular case means it is not a particular member of the family. Not a particular case means giving particular values to the arbitrary constants do not give you singular solution. Okay? Singular solution is a special surface which has got some relation with every member of the family. What is that relation? This particular surface actually touches every member of the family. Touches every member of the family. Remember that? In ODE also we had the similar kind of experience. Okay. Anyway, I will give you again the same example that we were discussing in ODE. Of course, in ODE we generally talk about a two-dimensional geometry. But in the case of three-dimensional geometry, if we extend the discussion, suppose I have a sphere, a three-dimensional object, a sphere. I have an external point, and this is discussion for those who did not attend my singular solution discussion earlier. Okay. Listen to me just 1 minute. We have a surface, a spherical surface, and I have a point outside my spherical surface. Okay. This point through which you draw tangent lines to the sphere. How many tangent lines can be drawn to the sphere from an external point? Infinitely many. Infinitely many. Instead, I will put in a very practical scenario. Because in three-dimensional geometry, we cannot express straight line as one single equation. Right? So instead of a straight line, now I will put in the different form. From an external point to the sphere external point, draw tangent planes to the sphere. Draw tangent planes to the sphere. How many tangent planes can be drawn? For every tangent line that you are drawing, you can draw a tangent plane actually. Obviously, right? It's the same thing. Okay. So you can draw infinitely many tangent planes passing through an external point to the surface of the sphere. Let all these tangent planes be my family of surfaces. Partial differential equation, it's more valid, right? Practically. So all these tangent planes be my family of surfaces. Okay. Now for this family of surfaces, I will have a differential equation. I will have a differential equation which looks like this. Okay. It will have a complete solution which looks like this. And the complete solution will contain all those tangent planes which will be of the form of ax plus by plus cz plus d equal to 0. Or since I have already used a and b, a dash x plus b dash y plus c dash z plus d dash equal to 0. Okay. Are you getting that? Now, for that family, the sphere becomes singular solution. Sphere again is a three-dimensional object. Okay. So when I compute singular solution for that family of tangent planes, what I am going to get is sphere. And sphere is that object which touches every member of the family, every tangent plane, right? And the sphere in fact do not contain any arbitrary constants because x square plus y square plus z square equals some constant I will get, right? And then sphere is not a member of the family because sphere is not a tangent plane. Sphere is not a tangent plane, therefore by giving particular values to the arbitrary constants in the complete solution do not give rise to sphere. It's a linear equation. In the case of tangent planes, it's a linear equation and sphere is a second degree equation. Are you getting that? So giving particular values to the arbitrary constants in the complete solution do not give me the sphere. Therefore, the singular solution is not a particular case of complete solution. But still, the equation of the sphere will satisfy the differential equation. That's the reason why we call it as a solution. The equation of the sphere will satisfy the differential equation. Therefore, it's a solution and hence we call it as a special type of a solution called as singular solution here. Getting that? Okay, fine. Now, finding singular solution. Procedure of finding singular solution. Procedure of finding singular solution. Let the complete solution of differential equation 1 be, let the complete solution of differential equation 1 be g of x comma y comma z comma a comma b equal to 0. G of x comma y comma z comma a comma b equal to 0. Equation number 2. I think we have already written that, right? Anyway. Partially differentiating 2 with respect to a and with respect to b separately. Partially differentiating equation 2 with respect to a and with respect to b. What we get? Dou g by dou a equal to 0 and dou g by dou b equal to 0. Let these equations be equations 4. Elimination of a comma b from 2 and 4 gives the singular solution. Elimination of a comma b from 2 and 4 gives the singular solution. Gives the singular solution. It's a similar experience that we had even in ODE also. If you remember, if you have a function of f of x comma y comma p equal to 0, partially differentiate with respect to p and elimination of p gives the singular solution. It's the same thing here also. It's the same thing. Okay. But only thing is, we don't have those complications that we had in our ODE, that extraneous loci, P discriminant relation, C discriminant relation, ECT square, EN square CQ, comparing both of them, the envelope, identifying the envelope and identifying the extraneous loci, all those headaches we don't have in partial differential equation. Okay. So we just need to partially differentiate the complete solution with respect to A and partially differentiate with respect to B and elimination of A comma B from 2, 3 and 4. From these two, actually you can identify two equations, two unknowns. A, B you can identify, A, B you substitute here, you will get singular solution. Right? Char-Pitts method. Any questions? Any questions here till now? Adu. C discriminant కాదు అవసరం లేదు ఇక్కడ అక్కడ ప్రొసీజర్ ఉంది ఇక్కడ ప్రొసీజర్ లేదు directly gives us singular solution directly. We don't need to go with the P discriminant or Q discriminant relations, not required. We don't have any such discriminant relations in the case of PDE. Also like Char-Pitts method. Okay. Let the given differential be the given differential equation be of the form f of x comma y comma z comma p comma q equal to 0. Be of the form. Continue. The Char-Pitts auxiliary equations are given by. The Char-Pitts auxiliary equations are given by. The way we had auxiliary equations of Lagrange's, we also have now Char-Pitts auxiliary equations. The Char-Pitts auxiliary equations are given by dx by fp. This is dou f by dou p. fp dou f by dou p. That means partially differentiation of this with respect to p is equal to dy by fq is equal to dz by pfp plus qfq is equal to dp by, in fact, if you see these, they in fact look like our Lagranges only. df actually dou f by dou p dp plus dou f by dou q dq. Okay, this is, one second answer. dz equal to dou z by dou x dx plus dou z by dou y dy. What was that actually? pp plus qq equal to r, right? Okay, anyway. I will discuss this. If it is in the standard form of Lagranges, these three look like Lagranges only. How? I will show you later. Okay, let me complete this first. Is equal to dp by minus of, in fact, this is Lagrange's one, which is extended to dp's and dq's by Char pits. That's the only thing. Anyway, I will explain that later. dp by minus, dp by minus of fx plus pfz is equal to dq by minus of fy plus qfz. qfz. Now, what we have to do here? These auxiliary equations I have to solve and determine what is P and what is Q. What is P and what is Q from these auxiliary equations? There are different ways of doing that. One way, if I need to get P, definitely I have to use dP. Okay, with some kind of multipliers, I will try to solve certain equation. Okay, when I am trying to solve equation, what I may get is P as a function of x's, y's, z's plus C1. Suppose if I get Q also I'll get some as a function of x's, y's, z's may not be there, might be there also, plus C2. Both of them I can directly substitute here, P and Q, which gives me a relationship between x's, y's, z's, C1 and C2, two arbitrary constants, two independent variables in the first order. Therefore, that actual relation satisfies the differential equation. Therefore, it is called a complete solution. That is one way. Second way of doing things is get P, substitute in this one, you will get Q also in terms of the same arbitrary constant. Okay, then there is one universal rule, dz equal to p dx plus q dy. This is quite obvious one, since z is a function of x and y, dz is always equal to dou z by dou x dx plus dou z by dou y dy. Get p and q both in terms of one arbitrary constant, substitute in this one, again integrate, you will get the second arbitrary constant also. Two arbitrary constant in two independent variable scenario in the first order gives rise to your complete solution. Accepted. But sometimes what people also do is, P they get from here with one arbitrary constant, Q they also get from here with second arbitrary constant. Both of them they substitute here. Again they integrate. You will get third arbitrary constant, which cannot be accepted as a solution of a first order partial differential equation with two independent variables. Obviously, you cannot have three arbitrary constant, right? In the first order with two independent variables, you cannot have a third arbitrary constant. But even if you have a third arbitrary constant, you have to reduce into two arbitrary constants by getting a relationship between C1 and C2 from this expression. Are you getting that?